2,400 square feet. I mean, picture a pretty comfortable four-bedroom house, but floating in low Earth orbit. That is the actual size of AST SpaceMobile's next-generation Block 2 BlueBird satellite phased array antenna. It's a completely staggering number, but it really perfectly frames the massive scale of the engineering challenge we're going to be looking at today.
Welcome to The Explainer. I am so pumped to take you under the hood of what is arguably one of the most ambitious telecommunications projects of our time. Today, our mission is to demystify the massive technical specs and the highly precise orbital parameters behind the very first global cellular broadband network in space. We are literally talking about bringing standard, unmodified smartphones online straight from orbit.
All right, let's quickly run through our agenda. We'll start with number 1. The size of the solution. Then 2, mapping the orbital grid. 3, the invisible frequency web. 4, the bent pipe architecture. And finally 5, connecting the unconnected. Let's just dive right in.
Section 1. The size of the solution. We absolutely have to start with the sheer physical scale of these literal space cell towers.
Because in the unforgiving physics of space communications, size isn't just some vanity metric. It directly translates to throughput and raw power. This contrast is just wild. AST's Block 2 is basically 35 to 40 times larger than a current Starlink V2 satellite. While Starlink sits around 65 square feet, the BlueBird spans about 2,400. And you might be wondering, why so big? Well, achieving true direct-to-device connectivity with that unmodified cell phone in your pocket means the satellite has to do all the heavy lifting to capture an incredibly weak signal from hundreds of kilometers away.
And AST SpaceMobile is definitely not holding back here. These satellites, which by the way are 95% vertically integrated right here in the US, pump out a massive 100 to 120 kilowatts of power. They're packed with custom, application-specific integrated circuits, or ASICs, designed to process 10 gigahertz of bandwidth per satellite. All of that generates up to 120 megabits per second in peak data speeds. That is an incredible 10 times the bandwidth capacity of their previous Block 1 iteration.
But what's truly fascinating is how you actually build an antenna that big. It's constructed from thousands of these tiny building blocks they call microns. Think of each micron tile as an independent, self-contained radio unit. They have their own tiny antennas, receivers, and even a dedicated solar panel and processing unit. They can listen and talk independently, almost like a massive fleet of highly advanced walkie-talkies working together. Plus, this phased array design lets them cancel out signals in other directions, which keeps the network incredibly clean and avoids interfering with other terrestrial spectrums.
Section 2. Mapping the orbital grid. So, we know these things are massive and powerful, but where exactly do they live? We actually have the documentary evidence straight from the Federal Communications Commission, mapping out the non-geostationary orbit parameters. You can clearly see the authorization for the initial deployment of 5 satellites operating right at a 520-kilometer apogee. It's the absolutely critical first step in laying down this orbital infrastructure.
Now, when you scale this up to the full 248-satellite constellation, breaking down the FCC filings reveals exactly how they create a continuous, global low Earth orbit grid. You've got these initial batches sitting at 520 to 530 kilometers with a 53-degree inclination. Then, the vast majority of the fleet, 192 satellites, sits a bit higher at a 690-kilometer altitude. They even have a specific batch of 28 satellites flying in a 98.1-degree inclination, which ensures absolutely comprehensive coverage from pole to pole. It is a meticulously planned orbital web covering the entire planet.
Section 3. The invisible frequency web. So how do they bridge that massive 500-plus kilometer gap down to your phone?
Before we throw a bunch of numbers around, let's just lock in 2 really vital terms. MNO stands for Mobile Network Operator. These are your everyday terrestrial carriers, companies like AT&T, Vodafone, Verizon, providing the wireless services you already use. Then we have MSS, which is Mobile Satellite Services. That's the dedicated satellite spectrum for two-way space communication. AST uniquely uses a wholesale partnership model here, leasing MNO spectrum so it just acts as a seamless extension of the network you're already paying for.
It's super interesting how the spectrum is logically sliced up to make all of this work seamlessly.
For the actual handset communication, they use lower bands, right around that 617 to 960 megahertz range. This is honestly the crown jewel of spectrum because low frequencies can effectively pierce through buildings and bad weather to reach your device. But then, for the feeder link, which is the heavy data backbone beaming back down to Earth stations, they use the high-frequency Q and V bands way up in the 37.5 to 51.4 gigahertz range. They even set aside dedicated UHF bands around 430 megahertz just for emergency telemetry, tracking, and control. It's really a beautifully orchestrated symphony of radio frequencies.
Moving right along to Section 4, the bent pipe architecture. All of this raises a massive engineering question. How does a single satellite process all that low-band handset data and high-frequency backbone data at the exact same time, without completely overloading? Well, this builds on our cell tower in space analogy with something called the bent pipe architecture. Instead of the satellite acting like some highly complex computer router up in space, it basically functions as an extremely powerful mirror. It takes your phone's signal, distributes power to amplify it, and literally bends it straight back down to partner carriers on the ground, without trying to route or process the core data on board.
Because the satellite offloads all that heavy data routing, your local mobile network operator gets to keep total control. They handle the core network, authentication, billing, device control, and rolling out new features. For you, the consumer, that means when you make a call, your phone honestly can't tell the difference between a local terrestrial tower just down the street or a giant satellite flying hundreds of kilometers above your head. It's completely seamless.
Which brings us to our final section, Section 5, Connecting the Unconnected.
Bringing all of this together, this specific combination of macro-physical hardware, precise orbital grids, and micro-radio frequencies has massive, real-world applications, not just for everyday consumers, but for governments and the 5 billion mobile subscribers worldwide. This isn't just about streaming a video while you're out hiking. For instance, Vodafone and AST are currently building a dedicated sovereign operations center in Germany. This center gets a specialized command switch to ensure secure European oversight. Even more importantly, it provides direct support for public protection and disaster relief, using seamless backhaul links to terrestrial 4G and 5G gateways to keep emergency responders online even if land-based networks get completely wiped out. Looking at the deployment timeline, this sci-fi vision is rapidly becoming reality. We saw the very first 4G and 5G space calls happen back in 2023. Now yes, the company did face a setback in May 2026 when a Blue Origin New Glenn rocket failed to reach the correct orbit. But the mission is pushing forward. Initial commercial launches are planned from Cape Canaveral this summer, and that paves the way for the mass deployment of those massive Block 2 BlueBirds starting in late 2026.
As we wrap up this explainer, I want to leave you with a pretty provocative thought. When a carefully coordinated network of 248 massive phased arrays, each one pushing out over 100 kilowatts of power and leveraging perfectly tuned frequency webs, finally blankets the entire globe in continuous cellular broadband, does the dead zone become permanently extinct? With this technology coming online so rapidly, are we quite literally about to witness a world where being unconnected is physically impossible? Really think about that. Thanks so much for joining me today, and keep looking up.